Okay, so welcome everybody to today's Corkin seminar. Today's speaker is Gabriel, and he'll talk about differentially large fields and Taylor morphisms.
Yeah, thank you to the organizers for inviting me. I'm very happy to be here. So today we'll talk about differentially large fields, and one of the tools that we use to study these differentially large fields, and a generalization and some results about this generalized notion that we've proven. So we'll start with a quick introduction to what these differentially large fields are and the relevance of, in particular, this twisted Taylor morphism. And then we'll move on to these generalized objects. So the class of differentially large fields is a generalization of the notion of largeness to differential fields which were introduced by Omar Leon Sanchez and Marcus Tressel. One of the main tools that you use to study these objects is known as the twisted Taylor morphism, which is constructed in the same paper where they introduce these fields. And this is a object which we can use to construct differential ring homomorphisms from non-differential ring homomorphisms in a uniform way, which allows you to preserve the differential structure in some sense. We'll see the definition in a minute. And essentially use this to show certain equivalences between existential closure properties and existence of points and things. And the focus of this talk later on will be a generalization of this notion, where we just define a Taylor morphism to be a certain functor in some sense, and we will see that it turns out what we get is quite rigid and in fact completely determined by a certain some slightly generalized twisted Taylor in some sense. Okay, so the standard disclaimer that I always give is that all the rings I talk about today are commutative and unital. The characteristic is not necessarily zero, but unless I otherwise say. And the differential rings that we talk about will be equipped with finitely many, in particular m, many commuting derivations. Okay, so what is a large field? So in some sense, a field is large if every variety over it, or if varieties over it have many points in some sense. So more precisely, this means that if every irreducible affine variety V over this field K, which has a smooth K point, has a Zariski dense set of K points. And equivalently, you can formulate this from a model theoretic perspective, and you can say that a field K is large if and only if it is existentially closed in the field of formal Laurent series K double bracket T. And this is as a field without like extra structure. And examples of large fields include many of the kind of nice model theoretic classes of fields, such as algebraically closed, pseudo-algebraically closed, real closed, Henselian fields, etc. And non-examples include things like the rational numbers, number fields, function fields, etc. And differential largeness is an analog of this in the context of differential algebra. And we say that differential field K is differentially large if it is large as a pure field, so that meaning if we forget the derivation, the underlying field is large. And for any differential field extension, L, if K is existentially closed in L as a pure field, then K is also existentially closed in L as a differential field. you can think of this as, we should probably remind some people what existential closure means, because I think we have some non-model theorists around. So a differential field, or differential in brackets, K is existentially closed in a differential K-algebra L if every finite system of differential polynomial equations and inequations with a solution in the upper object also has a solution in the lower one. And you can replace differential field with field, and you have the same notion for pure fields. And we can think of the class of differentially large fields as the class of fields equipped with a generic derivation in some sense. So if it is possible to have differential solutions to a certain system of differential equations, which is consistent with the field structure, then we can have it. Okay. So a few ways you can characterize these differentially large fields is firstly this existential closure condition, which is kind of analogous to the characterization for pure fields. So in particular, we have that this the differential field K delta is differentially large if and only if it is existentially closed in this K double bracket T with this delta plus d by dt derivation, where this bold delta is defined on this formal field of formal Laurent series by acting on the coefficients of a series. And in the case of one derivation, you can characterize it purely in terms of the existence of solutions to pairs of polynomial equations and inequations. So in particular, if we take two differential polynomials f and g in one variable, this is in the case of one derivation, with the order of f strictly greater than the order of g, and if we take a n plus 1 tuple, a bar, which is a solution to the, which is an algebraic solution to f, and by what I mean by this is if we take the differential indeterminates x, x prime up to x to the n, and treat them as algebraic indeterminates and plug this in, then we get 0. Such that it is not a solution to G, and the separand does not vanish on this point. Then we can also find a element B, which is a differential solution. And we can think of this as some kind of lifting of solutions from the algebraic to the differential setting. Okay. And examples of these differentially large fields include the analogs of the classes of fields we saw before. So differentially closed fields are the analog of algebraically closed fields. Closed order differential fields are the analog of real closed fields. And these differentially Henselian fields are fields with non-trivial Henselian valuations with a generic derivation in the sense of Kubines, Kovacic, and Poix. And many others. So you can have things like pseudo differentially closed fields, which are the analog of pack fields, etc. Okay, so the motivation for studying these abstract Taylor morphisms comes, of course, from analytic considerations. So by motivation, remember, if we take, say, a real smooth function, f, we can think of it modulo some analytic considerations as a Taylor series around 0. So you can take the derivatives of its of this function and plug them into this Taylor series, and we essentially have some encoding of the information of that this function has around 0. And if you think of this from an algebraic perspective, we can think of this map taking smooth functions, the map from the ring of smooth functions over R, equipped with the usual derivation, to the ring of power series over R with its usual formal derivation. And the map which takes a function to its Taylor series is a differential R algebra homomorphism. And the classical Taylor morphism is a generalization of this to kind of arbitrary differential rings and ring homomorphisms. So before we continue, we should fix some notation. So bold symbols denote a tuple of m derivations or indeterminates. For example, this bold delta is this m tuple of deltas, necessarily commuting because we fix the old derivations commute. And this bold t is just a tuple of m indeterminates, t naught up to t m minus 1. If I write bold 0, this is the m tuple of trivial derivations. So I'll sometimes say things like a constant ring, and by this I just mean a ring equipped with the tuple of 0 derivations. And for notational convenience, we will use a lot of multi-indices. So a multi-index is just a m tuple of natural numbers. Delta to the alpha and t to the alpha denote this composition of derivations and this product of indeterminates, respectively. And on multi-indices, we have the partial order given by the product. So that is, if I take two multi-indices, we say that alpha is less than or equal to beta, if and only if this is true for every component. And we can add and subtract these things component-wise. The factorial denotes the product of the factorials of the components, or the entries, and the binomial coefficient is defined in the same way. Okay. So now we'll talk about this generalization, this classical Taylor morphism. So if we have K a Q algebra and some differential ring A, and phi from A to K a ring homomorphism, then this classical Taylor morphism is just the differential ring homomorphism T phi from this differential ring A to the formal ring of power series in M indeterminates over K, given by just taking the Taylor series of every element via this ring homomorphism phi. And you can write it out and check that this is actually a differential ring homomorphism. And we'll see that the previous map that we talked about, which takes a smooth function to its Taylor series at 0, is precisely the result of applying this Taylor morphism to the evaluation map, which takes a smooth function to its evaluation at 0. Okay. So the problem which Leon Sanchez and Tressel encountered with using this is that you will find that if we already have a derivation k on k, then this k double bracket t d by dt is not naturally a differential k algebra because, for instance, k is constant in this ring. So it turns out that it is possible to construct some twisting of this Taylor morphism, which allows you to preserve this differential structure on K. So now we fix K delta, a differential Q algebra, and again, a differential ring, now a partial. This delta plus d by dt is the m tuple of derivations on this formal power series ring, which is given by the sums, the component-wise sums. So delta naught plus d by dt naught up to delta m minus 1, d by dt m minus 1. You can check that they still commute. And in particular, now if we use this ring is a differential K delta algebra with the structure map, which is given by just the inclusion of K into its ring of formal power series. And we can construct this twisted Taylor morphism object, which we denote by T star. So if we fix a ring homomorphism phi from A to K, then the twisted Taylor morphism of phi is given by this formula. So it's the series where the coefficients are given by this alternating binomial sum. So I will say that this is not coming out of nowhere. There's a good reason for this formula. And we'll see kind of a similar construction later on. But essentially, you construct a map that goes from this object to this object, which takes the map, takes the Taylor morphism to this. And in particular, this object satisfies two, in my opinion, nice properties. So firstly, if we take something that is already differential, so suppose we have phi that goes from A to K, and this is already a differential ring homomorphism, then if we take T star of this, this is precisely given by the inclusion of the composition of phi with the inclusion, and that is to say, this T star in some sense preserves these differential maps. And secondly, if we have two differential rings, A and B, and we have two differential ring homomorphisms, phi from A to K and psi from B to K, and a differential ring homomorphism chi going from A to B, such that the triangle commutes. So I guess I can draw this. So if we have A going to K and B going to K, this is psi and this is chi, such that this commutes. And if chi is differential, then applying T star preserves this, so this commutativity. So if that commutes, then the resulting triangle after applying T star, this is K bracket T, also commutes. Right. I say it's functorial because this is equivalent to being functor between some category, which you can probably imagine. I won't explain exactly what it is, but you can. It's not difficult to cook up something like this. So in particular, if we have that this ring A is already a differential K delta algebra, and if phi is a K algebra homomorphism, then this T star phi going from A to L, sorry, this should be K double bracket T, is then a differential K algebra homomorphism. Because you can replace this with K, and this is the structure map, and the commutativity of the triangle implies that you preserve K algebra structures. And as a final remark about this twisted Taylor morphism, if this delta on K is non-trivial, so in contrast with this, this classical Taylor morphism T that we saw a few slides ago doesn't preserve this K algebra homomorphism property, at least if you take the usual K algebra structure on K double bracket T. Okay. Oops. how do I clear this? Oops. Uh, 1 second. Okay. Okay. Now we define a generalized Taylor morphism to be essentially just a map which satisfies the previous two properties that we noted about the twisted Taylor morphism. So precisely, let K be a differential ring, and let L be a differential K algebra where we denote the structure map of L by this eta L. A K Taylor morphism for L is a map, which will denote T, which sends a pair, a phi, where A is a differential ring, and phi from A to K is a ring homomorphism, to a differential ring homomorphism T phi from A to L, which satisfies two properties. So firstly, if phi is a differential ring homomorphism, then T phi should be precisely the composition of this eta L with phi. And secondly, if we have the same commuting triangle as before, so phi A to K and psi B to K ring homomorphisms, and chi from A to B is a differential ring homomorphism which makes the triangle commute, then the resulting triangle after applying, that should just be T, there's no T star here, should still commute. Okay. And if there exists a K-Taylor morphism for L, then we say that L admits a K-Taylor morphism. Okay, and some examples. So everything we've seen so far is an example of a Taylor morphism in this generalized setting. So firstly, for example, we take a differential Q algebra K delta. The twisted Taylor morphism that we saw before is a K delta Taylor morphism for this differential K algebra. So K double bracket T with this delta plus D by dt. If we take a constant Q algebra, that is a Q algebra equipped with the zero derivations, this classical Taylor morphism T turns out to be precisely a K0 Taylor morphism for K double bracket T with D by dt. And in fact, this is actually just a special case of this one, where you take delta to be 0. And there is something that I call the Hurwitz morphism, which we will see later. And this will work in, which is a Taylor morphism for constant rings of arbitrary characteristic. And for the rest of this talk, essentially the objective is to characterize the class of differential K algebras which admits such Taylor morphism, and we will also give a concrete description of what these Taylor morphisms look like. Okay. So before we do that, actually, we'll give a little bit more justification as to why we are doing this. The hope is essentially we can use this new technology to study these differentially large fields in a slightly more general setting, so in particular in positive characteristic. So for example, we can also characterize differential largeness basically in terms of just no twisted here. In terms of these Taylor morphisms. So for example, let K be a differential field of characteristic 0, which is large as a field. Then we have that K is differentially large if and only if there exists a differential K algebra L, which admits a K Taylor morphism with K existentially closed in differential rings, as differential rings. So essentially, this is analogous to the previous result, which said that K is differentially large if and only if it is existentially closed in this K double bracket T. Because in that case, you get that K is large for free because of the existential closure. And essentially, the proof goes in exactly the same way. And yeah, equivalently, you can also say that there is an elementary extension of K which admits a K-Taylor morphism. Okay, and you can also generalize a construction of these differentially large fields in a similar way. So if we have a directed system of differential fields of characteristic 0, and if these Fij's are differential embeddings such that each of them is large as a field, and for each, so if we take two elements in the chain, then the lower things are existentially closed and the upper things as fields. And for each thing in the chain, there is something above it such that the thing above it admits a K-Taylor morphism over the lower one. And then if you take the directed limit of this system, then this will be differentially large. And there's a kind of analogous proof in the paper of Leon Sanchez and Trussell, which essentially just talks about this K-dot bracket T instead of these Taylor morphisms, but the proof goes in more or less the same
way. Gabriel.
Okay. Yeah.
Just to clarify, that's your proposition or is it Omar's? Or
this is my proposition, but it's more or less the same as Omar's proposition, except yeah. Okay, so now we'll talk about this promised example of this Hurwitz morphism in positive characteristic. So we first note that if we remember back to earlier, the classical and twisted Taylor morphisms don't really work in this positive characteristic setting because you have to divide by these denominators which die in characteristic P. Right. And so there is this construction, which we call the Hurwitz morphism, constructed by Kiger in the 90s, which works for all differential rings. And to do this, we replace this ring of formal power series with this ring of Hurwitz series, which we'll explain. So let's first let K be a ring of any characteristic. It doesn't need to be a field or a domain or anything like that. The ring of Hurwitz series, and we'll say in M indeterminates, because we have M indeterminates, is as a group, as an additive group, the same as the ring of formal power series, but we replace the multiplication, the usual multiplication, with this one. In particular, you'll notice that there's these binomial coefficients inside the multiplication. And the benefit of doing this is that you have a very simple differential structure on it. So this ring of Hurwitz series is naturally equipped with a tuple of m derivations, which we denote by dk. And this is given precisely by shift in the indices. So to make it simpler, if you think of these as, if you just think of the one derivation case, each Hurwitz series is just, you can think of it as just a normal power series, and the derivation is given precisely by shifting all the coefficients down by 1. Okay. And there is a kind of analogous construction to the classical Taylor morphism in this setting. So if we let, again, K be a ring, A delta a differential ring, and we take a ring homomorphism phi from A to K, then the Hurwitz morphism of phi is the differential ring homomorphism, which we denote by H sub phi, from A delta to this ring of Hurwitz series with these shift operator derivations. And it takes a element A to the series where the coefficients are given precisely by the derivatives of A via this morphism phi. And you'll notice there are no denominators to divide by now. We essentially have just encoded the jet of A in the coefficients of the series. Right? If we consider K as a differential ring, which we equip with the trivial derivation, then this H is a K0 Taylor morphism for this ring of Hurwitz series, H of K. And something that's kind of interesting is that in the case where K is a Q algebra, this ring of Hurwitz series is actually isomorphic to the ring of formal power series. And what you get from this Hurwitz morphism is precisely the same as what you get from the classical Taylor morphism before. And the main structure theorem for these generalized Taylor morphisms is that we have a universal object. Okay, let's fix K a differential ring. So there is a differential K algebra, which we denote by K star, and a K Taylor morphism, which we denote by T upper K for K star, such that for any differential K algebra L, which admits a K Taylor morphism T, there is a unique differential K algebra homomorphism theta from K star to L, such that for any differential K algebra A and K algebra homomorphism phi from A to K, we have that this T sub phi is precisely the composition of this TK phi with this theta. So I'll say a few words about how this is proved to give some intuition as to why this is true. So it turns out that you can construct some diagram in the category of differential K algebras such that every K Taylor morphism corresponds to a co-cone of this diagram. And if you take the co-limit of this thing, this will turn out to be precisely this universal Taylor morphism here, this TK. And the unique map from this co-limit to any other K Taylor morphism is precisely this K algebra homomorphism theta that you get out here. And so we call this T upper K, this the universal K Taylor morphism. And we will give a concrete characterization of this object, which will turn out to be a twisted version of this Hurwitz morphism in a similar way to the twisted Taylor morphism. Okay, so how do we characterize this thing? It turns out you can do it in terms of something which I call an evaluation map. So if we have K differential ring, L a differential K algebra with T a K Taylor morphism for L, an evaluation map for this Taylor morphism T is a K algebra homomorphism, not necessarily non-differential, which we call EV from L to K, satisfying, firstly, for any differential ring A and ring homomorphism phi from A to K, the composition of EV with a Taylor morphism of phi is phi. And secondly, the Taylor morphism of this evaluation is precisely the identity. The reason, so the motivation for this is essentially that if you have an evaluation map for this T, then this evaluation is essentially a two-sided inverse to this Taylor morphism. So the first condition says that evaluation is a left inverse, and the second one essentially encodes the fact that it's a right inverse as well. And if such an evaluation map for a Taylor morphism exists, we say that this T admits one. And so some examples of these evaluation maps are, well, firstly, if we take a constant Q algebra K and T to be the classical Taylor morphism for the power series ring, then the evaluation at 0, so taking a series to its coefficient constant term, is an evaluation map for this classical Taylor morphism. And the same map actually works also for the twisted one. And again for the Hurwitz one as well. Although I guess this is a different ring, so it's not exactly the same map, but you can check easily that this remains a K algebra homomorphism, and then that this works basically. Okay, and it turns out that being universal is completely characterized by the existence of one of these evaluation maps. So if we let, again, K be a differential ring, K-Taylor morphism T is isomorphic to this universal K-Taylor morphism if and only if it admits an evaluation map. And as a consequence, we have that this Hurwitz morphism and the twisted Taylor morphism are precisely the universal Taylor morphisms for, firstly, a constant ring, and secondly, differential K-algebra, respectively. So we know what the universal object looks like for constant rings and also for differential K-algebras, but not yet in general. And that's what we will construct now. So what we will do is we will twist the Hurwitz morphism in a way which is analogous to the twisting of the Taylor morphism by Leon Sanchez and Tressel. And we'll also show that this thing has an evaluation map and therefore is universal. So fix a ring, K, and we let H denote the Hurwitz morphism, which we consider as a K0 Taylor morphism for this untwisted Hurwitz series ring. And a little bit of notation. If we let delta be a family of commuting derivations on this K, we write H upper delta plus dk sub EV for this Hurwitz morphism applied to the ring homomorphism EV, which is considered as a ring homomorphism between these differential rings. Is that clear? Okay. And we say that two families of commuting derivations, delta and partial, commute of derivations on the ring K commute if all of the derivations within these two families commute with each other. And finally, for a family of commuting derivations delta on K, we also write delta for the family of derivations on H of K, where each of these deltas acts on the coefficients of the series by delta. So in particular, if we apply delta I to this series, we simply apply it to all of the coefficients of the series. Okay. So the main lemma of this construction is that if we suppose that delta and partial are commuting families of commuting derivations on this ring K, then what the result of taking H of EV with the ring on the ring where we take the derivation delta plus partial plus dk is equal to the composition of taking them separately. And in particular, for any family of commuting derivations delta on K, this H upper delta plus dk EV is a isomorphism of differential rings. This should be H of K, sorry. with the inverse given by taking the negative of this derivation. Okay. And now these are the ingredients which we need to define this twisted Hurwitz morphism. So now we let K delta be a differential ring, so without restriction at all. For any differential ring, a partial and ring homomorphism phi, we define the twisted Hurwitz morphism of phi to be H star phi, which is the composition of H phi with this isomorphism that we have just constructed. And so now this is a map from a partial to this H of K with this delta plus dk derivation. And if you explicitly compute what this is, we get that a very similar formula to what we saw before without denominators. And you'll also find that there's an isomorphism between this. In the case of a differential Q algebra, this is actually essentially isomorphic to the twisted Taylor morphism before. And the main theorem is that for a differential ring K delta, the twisted Hurwitz morphism H star is the universal K delta Taylor morphism for this ring, this twisted Hurwitz series ring. And I guess as a remark, this gives you essentially what every K Taylor morphism is, and that it is the image of precisely this twisted Hurwitz morphism in some H of K algebra, differential H of K algebra with this derivation. Okay, and I guess as a, how long do I have? A little bit. It turns out that this twisted Hurwitz morphism and this universal Taylor morphism thing is the result of some adjunction in category theory. And this universal Taylor morphism is actually the natural bijection of Homsets, which comes from some adjunction. So firstly, we define this category D ring subring, which is the category whose objects are differential rings, and the morphisms are just ring homomorphisms. So the morphisms are the result of just ignoring the differential structure on these rings and just taking ring homomorphisms. And we write I for the inclusion of the category of differential rings into this funny category. And it turns out that you can construct a functor by taking every differential ring to its ring of twisted Hurwitz series. So if we have K and L differential rings and a ring homomorphism between them, there is a unique differential ring homomorphism theta star from K star to L star, such that for any other differential ring A and ring homomorphism phi, we have applying the universal Taylor morphism of L to theta composed phi is equal to applying composing theta star with the universal K Taylor morphism of phi. And as a result, the map that you get by defining, sending objects, so differential rings K to K star and morphisms by this star functor is in fact a functor. And the commutativity is essentially given by this. And I guess one remark is that if we have two differential rings, which are isomorphic as rings, then K star is actually isomorphic to L star under this by this lemma. Okay, and one last thing. So the functor f that we just constructed is precisely the right adjoint to this inclusion from the category of differential rings to this funny category. And if we take a differential ring A and a differential ring K in this category, the natural bijection of Helm sets is given precisely by this universal Taylor morphism Tk, and the inverse is given by composition with its evaluation. So yeah, if we take a these are precisely the natural bijections of Helm sets. Okay, I should probably just say a little bit about what we plan to do with this. Essentially, as I said before, we want to study these differentially large fields in positive characteristics. So we hope to be able to use this twisted Hurwitz thing in some way. There's a few things to be done because this Hurwitz ring is not generally a domain, for example, in positive characteristic. So you have to work around this somehow. And yeah, I think that's more or less all I have to say for today. Yeah, thank you for listening.
All right, thank you, Gabriel, for this nice talk. Do we have any questions or comments? Just unmute yourself and ask, or you can also type in the chat if you prefer.
I might ask, sorry, excuse me. Is there any analogous largeness and also all these constructions for difference fields?
For difference fields, to be honest, I don't really know. I've kind of vaguely thought about it, but it's at least I personally haven't seen any literature on this, and I don't really know enough about difference fields to comment intelligently, I think.
Okay, any other? Oh, sorry.
Just a very minor point. When you order the indexes, multi-indexes, you're using a product order, is that correct?
That's correct, yeah.
Okay, thank you.
Any other questions or comments? Okay, so if not, then let's thank Gabriel again. And I'm looking forward to seeing everyone again next week.
Thank you.
Thanks, take care.